All right, so I think this is recording. Let's take a look at these three equations. They're not quadratic equations, but they are quadratic in form. If we look at number 6 here, this is set up and is equal to 0, that this x squared, this exponent 2 is half of 4. Now, the first thing that I notice about this problem is that we have a greatest common factor of 5, that we can divide all of these terms by 5 and reduce the problem for us here. So 20 divided by 5 is 4. 25 divided by 5 is 5. 5 divided by 5 is 1. 0 divided by 5 is 0. So that just makes the numbers smaller and easier for me to work with. Again, we're going to do a change of variable. We're going to let u equal this middle term, the variable, this middle term, x squared. And if we square both sides of this equation, then we're going to let u squared be x to the fourth. So although this original equation is not a quadratic equation, through this change of variable, everywhere we see x to the fourth, we replace it with u squared. And everywhere we see x squared, we replace it with u. And now I do have a quadratic equation. Let's see if we can factor this. If we can't factor it, we can use the quadratic formula. With our x method, our middle term there is -5. The first term times the last term is 4u squared. If we come up with two values that multiply together to give us this top value, but add together to give us the bottom one, then if we write the results in the form of a table and use this table to help us factor this trinomial, the first term and last term of the equation go along one diagonal. The two values we found in our x go along the other diagonal. And here, when this is positive, each of these on the outside here are going to be negative, because a negative times a negative is a positive, and these are prime with respect to each other. The only thing they have in common is that -1. Now here, when I look at this, what they have in common is the variable u, and vertically here what they have in common is 4u. So I can easily check that 1u times 4u is 4u squared, and I can come in and check my table just to make sure that I factor that correctly. It looks like I did. So on the left-hand side here, if I write u minus 1, and across the top, 4u minus 1, we can split this into two equations. We have a zero product theorem, that if you have a list of real numbers whose product is 0, then you have at least one 0 in the list. So we know that either u minus 1 is representing 0, or that 4u minus 1 is representing 0. This is a two-step equation. Add 1 to each side and divide by 4. But now here's the part that students can sometimes forget, and that's to go back to the original variable. This u, remember, through a change of variable, that's how we were able to set it up as a quadratic. U was really representing x squared. So if x squared is equal to 1, then x could be positive or -1. If x squared was representing 1/4, then x could be positive or -1/2. So there's our solutions to this equation. Now, what about this middle one here? Is this quadratic in form? Well, look at this 1/5. That's half of 2/5. So yes, it's quadratic in form. We can, and this is set up where it's equal to 0, and I see no common factor like I did before. So I can jump right in and do my change of variable. I'm going to let u equal this middle variable here, the x to the 1/5. And if I square each sides of this equation, I get that u squared is going to be x to the 2/5. So I can rewrite this equation as u squared minus 2u plus 1 is equal to 0. And this I can easily factor into u minus 1 quantity squared. And here, 1 minus 1 gives you 0. U has to equal 1, or take the square root of both sides and go through it that way. But you can see that 1 minus 1 gives you 0. That if u is equal to 1, remember I want to replace u with x to the 1/5 power. But if I raise each side to the 5th power, then 1 to the 5th power is just 1. So I have 1 as my solution to this. And you can, by substitution, you can see if this is 1, 1 minus 2 plus 1 is equal to 0. That you can easily see that checks. All right, so let's look at this last one here and see if it's quadratic in form. I believe it is. We have x to the 3rd power minus x. We'll see this exponent 3, half of it is 3/2. So yeah, this is quadratic in form. So we can do a change of variable. We can let u be this middle variable, x to the 3/2. If you square each side of this, then u squared is equal to x to the 3rd. We can replace x to the 3rd with u squared. Since this leading coefficient is 1, this is very easy to factor. It splits into 2 equations where 3 minus 3 would give you 0. Negative 2 plus 2 would give you 0. If we replace u with 3/2, x to the 3/2, I'm sorry. And over here, with this index, with this denominator being 2, remember this is the square root of x cubed. This has no solution. This provides this is extraneous. This x to the 3/2 power will never result in a negative number. Now over here, let's see if I can shrink everything up a little bit. I'm just going to come along and see if I can't outline the whole thing. Yeah, it worked out kind of nice. All right, so if I have this x to the 3/2 and I raise this to the 2/3 power, then this 3, I have to raise it to the 2/3 power. When you have a power raised to a power, you multiply the exponents, and 3/2 times 2/3, these are reciprocals of each other, and the product of reciprocals is just 1. So I have the x is equal to 3 to the 2/3 power, and that's my solution. Some people might write this as the cube root of 3, and then you could say squared, or you can have this squared be inside that radical, and this could be the cube root of 3 squared, which is 9. So you've got multiple ways that you could write that answer. I'm just going to leave my answer like this. So I hope that helps, and I will talk to you later.